Hi everybody, this video is on section 1.9, exact differential equations. So I want us to start by considering a first order differential equation. And we're going to assume that it has no specific form. So in other words, any differential equation looks like this. M of xy plus n of xy times a derivative is equal to 0. Okay, so this is just a first order differential equation, not necessarily linear, not necessarily homogeneous of degree 0, not necessarily any form that we are familiar with, okay? We can write this in differential form. What does differential form look like? It looks like this. Okay, now I know it doesn't look like this makes sense because we've got a dx and we've got a dy there. But remember, this really just means this, okay? They mean the same thing. So the dy dx really is truly attached to the n that's right there. Okay? Let's go ahead and give this guy a name. We're going to call it star so that we can refer to it in a second. I want to give you guys a definition. So the star that we just wrote down is called an exact equation if there exists a function phi of xy such that m is equal to the partial of, oh, you know what? I should write this as a capital phi. Yeah, I should write this as a capital phi just because that's the way your book writes it. So let me not make you guys learn a new or a lowercase. I was using a lowercase phi a second ago. So there exists a function phi such that m is equal to the partial of phi with respect to x, and n is equal to the partial derivative of phi with respect to y. Okay? So this is what it means for a differential equation to be called an exact equation. It's just called exact if this m and n that you see, these two functions, are both partial derivatives of some two-variable function called phi. Now let me give you an example. So let's look at the following differential equation. Tan y dx plus x secant squared y dy equals 0. So this differential equation is exact. Okay? Why? Since for phi of xy equals x tan y, what's the partial of phi with respect to x equal to? Well, if you take the derivative of x tan y with respect to x, you just get tan y, and that's equal to m, right? We notice up here that this is m and this is our n. And what's the partial of phi with respect to y? Well, the derivative of x tan y with respect to y is just x secant squared y, which is equal to n up here. Okay, so therefore that differential equation is exact. Now, why do we care that a differential equation is exact? The good news is we can solve such an equation right away. So notice we can now solve the above differential equation. Why is that? Well, let me go ahead and call this differential equation star. Star becomes the following. Okay, we're going to write the following down. This is actually equal to the derivative of x tan y. Why is that? Well, I'm going to show you guys why this works in a second, okay? But I want to first solve the differential equation and then show you that we end up with the exact same thing, okay? So I've just written this down, and again, I will show you guys where this comes from in a second. But if we agree that this is true, if we can think of the dx as being here, right? So if we now integrate both sides, what do we end up with? Well, on the left, we just get x tan y, and on the right, we get 0 plus c, which is just c. Okay, so this becomes our answer. Okay, this is our solution to our differential equation. Or, if you want to, you can also actually solve for y. So what would y be? We could write y as arctan of c over x. Okay. So you could write the answer either way. Now, how would we check that this actually works? So let's go ahead and check the solution here. Let's take our solution. Remember, we've got x tan y equals c, and we're going to take the derivative with respect to x of both sides. If we do that, we end up with, well, we need the product rule and the chain rule on the left side. We get the derivative of the first times the second plus the first times the derivative of the second. It's secant squared y times dy dx. And I get equals 0. Okay, so this is what I get. And if I want to go ahead and write this in the other form, I can just multiply both sides by dx here. And the form becomes tan y dx plus x secant squared y dy is equal to 0. So notice we got the exact same differential equation that we started with. Okay? Therefore, knowing that a differential equation is exact means that it is theoretically possible to find the solution. Of course, it involves having to find phi, right? Because phi is the key here. That ends up being the exact solution. Okay, so let's go ahead and define some terminology here. That guy phi has a specific name. So definition, if the derivative of phi is equal to m dx plus n dy, we call phi of xy a potential function for the differential equation m dx plus n dy is equal to 0. Okay? So this is if phi satisfies this condition. We call it a potential function for the differential equation. Now, are all first-order differential equations exact? The answer is no. So not all differential equations are exact. So how can we tell if it is? Well, the answer comes in this following theorem. And this will seem familiar to you because you guys dealt with this in Calculus 3, in multivariable calculus. So let me write down the theorem here. This is called the test for exactness. Okay. What is the test? So m dx plus n dy is equal to 0 is exact if and only if. So the test is the partial of m with respect to y is equal to the partial of n with respect to x. Or another way of writing that down is my is equal to n little x. Okay, so if that condition is true, then that's how you check. So if that condition is true, then that means it is exact. And remember, all it means for something to be exact is that there exists a potential function. We still haven't gone over how you actually find it. Okay? So let's look at that last example. So note, in the last example, remember our problem in the last example was tan y dx plus x secant squared y dy equals 0, right? Remember, this is our m, and this whole thing is our n. So partial of m with respect to y is equal to secant squared y. Partial of n with respect to x is also secant squared y, and these two are equal to each other, right? My is equal to nx. So note, that would have been a way, if we were just given the differential equation, that would have been a way to tell if it was exact. Okay, so this is the test for exactness. Okay, so how do we find the potential function if we know that it exists? So the way we do this is the reverse of partial differentiation, which is, I like to call it partial integration, but you guys actually have already done this in Calculus 3. Okay, this is a process that you learned in that class, so I'll just be reminding you guys of that process, and we will go over it in detail, okay? So let's go over the steps. So steps for solving an exact differential equation. Remember, you're going to assume that you're starting off with some differential equation star, which looks like this: m dx plus n dy is equal to 0. Okay, so step one. Step one, of course, is going to be first to check to make sure it actually is exact, okay? Because on an exam or something like that, you're not going to know unless it passes the test. So check if star is exact by verifying that my is equal to nx. Okay, this is what you have to check, right? Now, assuming that it is, you move on to step 2. So step 2, I'm going to say find the potential function phi of xy by using, I call this partial integration. Okay, how does partial integration work? Well, think about it. If we know that the partial of phi with respect to x is equal to the m function, then this means that we can find phi by taking the integral of the m function with respect to x. However, when you do that, you're going to get not plus c, but you're going to get plus some unknown function of y. Okay? Next, partial of phi with respect to y, if that's equal to n, then that means that phi is equal to the integral of n of xy with respect to y plus some other function of x. Okay, now what happens is you can now take these two guys and set them equal to each other, and this allows you to find phi. Right? Because these unknown functions are going to be what you're looking for. So if you know what these two things are and you set them equal to each other, these two giant expressions, then you can find the h of y or the g of x, okay? Finally, your differential equation is going to become d phi is equal to 0, which means that phi of xy is equal to c is the general solution to star. Okay, so once you find the potential function, just set it equal to c, and there you go. That's your general solution. Okay, let's first practice actually solving, let's practice testing some differential equations to see if they're exact. So, example. Are the following differential equations exact? So first one, 2x e to the y dx plus x squared e squared e to the y. X squared e to the y plus cosine y dy equals 0. So question, is this exact? Remember, this is m and this is n, right? So let's do the test, right? What's the test for exactness? Partial of m with respect to, y is equal to just 2x e to the y. Partial of n with respect to x if you take the partial derivative of that guy with respect to x, it's just 2x e to the y because the cosine y term goes away. And these are equal to each other. So it is exact. Okay, let's try another one. X squared y dy plus, or let me put a minus in there, minus x y squared plus y cubed dy is equal to 0. Okay. So is this guy exact? So let's go ahead and label this, right? This would be our m, and actually this entire thing, including the negative sign, would be the n. Okay, so what is my equal to? This would just be x squared, right? And what is nx equal to? Remember, we've got the negative sign there, and if we take the partial derivative with respect to x, we actually get y squared. Okay, and these two guys are not equal to each other. So since my is not equal to nx, it is not exact. Okay, so of course this is just to illustrate that not every first order differential equation is exact. Some are, some are not. Okay, but we do have a way to solve all exact differential equations now, as long as the integration isn't too tricky. And of course the problems that we do in this class, the integrations are never going to be super tricky, okay? All right, so let's go ahead and try an example. So I want us to solve the differential equation, and it's going to be y over x dx plus 1 plus ln of xy dy is equal to 0, and x is a positive variable. Okay, so this is going to be our differential equation. So we are going to test for exactness. So let's do the test for exactness. Remember, this right here is our m, and this right here is our n. So we're going to take the partial of m with respect to x. Remember, this means treat y like a constant. Okay, so if you differentiate that guy with respect to, I don't know why I keep writing that. This is my, right? Do the partial of m with respect to y, and that's just 1 over x, right? And what is the partial of n with respect to x? Well, the 1 goes away, and so we would need to use the chain rule to differentiate ln of xy. This is going to be 1 over xy times the partial derivative of xy, right? Because that's the chain rule. With respect to x is just y. But this is just 1 over x. Okay, so because these two are the same, so since y is equal to nx, let me call it star here. Star is exact. So now we're going to find the potential, okay? Remember, all of that was step 1. So if I were to label it as step 1, there it is. So what would step 2 be? Step 2 is going to be to figure out the potential function. So we're going to find phi. So how do we do that? Well, we have to remember that the derivative of phi with respect to sorry, I should be writing partial derivatives here. The partial derivative of phi with respect to x has to equal y over x, which means that phi has to equal the integral of y over x dx. So how do you integrate that guy with respect to x? So this is just going to be y times the natural log of x, right? Y, because the y can basically just pull out of the integral, right? Y ln of x, but remember this is plus some unknown function of y, because we integrated with respect to x, so this means any function of y would get killed off by the antiderivative. So we have that, and now let's do the other one. We know the partial derivative of phi with respect to y has to equal n, which is 1 plus ln of xy, which means that phi is equal to the integral of 1 plus ln of x y dy. So when you integrate that guy with respect to y, let's see what we get. So we end up with y plus, now the integral of ln is a funny one, okay? I'm not sure if you guys remember how to integrate that, but what might help is instead writing this as, using rule of logs to separate this. This is ln x plus ln y, right? And so what would the integral be? Well, first, the integral of ln x with respect to y is just going to add an extra y in there, right? Because ln x acts like a constant here. So this is going to become plus y ln x. Now the integral of ln y is y ln y minus y. Okay, why is that? This is just a consequence of integration by parts. Okay, if you integrate ln y, you get y ln y minus y. Okay, so what do we get here? Well, the minus y and the y are gone, so we actually end up with y ln x plus y ln y. Okay, so now what? Let's not forget that this also includes plus an unknown function of g of x, right? This is like our plus c, plus g of x. And now we take this guy and this guy. Remember, these are both phi, right? These are both phi. So we take that guy and we set it equal to this guy. And when you set it equal to that guy, you realize that h of y must be y ln y. Okay? So if you set the two equal to each other, you get the following. This implies that h of y is equal to y ln y, and g of x is 0. Right? Because there are no functions of x in the other piece, but you set these two pieces equal to each other, and so we end up with the following. This means that phi of xy, the potential function, is equal to just y ln x plus y ln y. Okay? So now we're ready to write down the solution, okay? This means that d of y ln x plus y ln y is equal to 0, or the solution, if we integrate both sides, we get y ln x plus y ln y is equal to c. This guy is the solution to the differential equation. So you can see that all the work boils down to being able to find this potential function, right? By the way, there is another way to write this answer down, okay? This entire function over here, if you factor out a y, this just becomes ln x plus ln y. which is just ln of xy. So if you want to write the answer like this, you can, okay? It's the same thing. It does look a little cleaner that way, right? Okay, I wanted to illustrate another step or wrinkle in the problem. This is the easy type of problem, but you might actually get some trickier ones. So let me just write a new definition here. The integration factor, remember the integrating factor idea that came in with first order linear differential equations? These problems might have an integrating factor as well. So let me give you guys a definition. A function I of xy, which is not going to be 0, right? It's not allowed to be 0, is called an integrating factor for the differential equation m dx plus n dy is equal to 0. So, oh, sorry, I didn't write the whole word out. Let me write it out. Integrating factor for the differential equation if multiplying, let me call this star, if multiplying star by I of xy makes it exact. So here's what we're saying. What we're saying is that suppose we do not have an exact equation. However, if we multiply it by a particular function, we turn it into an exact equation. That function is called an integrating factor. Okay, so question then. Question 1, how can we tell if a differential equation has an integrating factor? Question 2, if it does, how do we find it? So the good news is that there is a modification of the above method for doing the integrating factor. So let's write down a theorem which is going to answer both of these questions. So theorem. Consider the differential equation. Again, I'm going to call this star. M dx plus n dy is equal to 0. So here is the theorem, okay? The theorem says if taking my and subtracting nx and then dividing by the n function, okay, if that's equal to f of x, a function of x only. This is what we mean by that. If doing my minus nx and then dividing by n gets rid of all the y's and you only have x's left, then it's going to have an integrating factor, and I will even tell you how to find it. Then I of x is going to be e to the integral of this f function. This guy is an integrating factor for star. Now, what's the second part of this theorem? Suppose that doesn't work, right? Let's say you do my minus nx, you divide it by n, and you do not get a function of x alone. Well, you can also do it the other way. What if my minus nx divided by m is equal to g of y? A function of y only. Then I of y, which is equal to e to the negative integral of g of y dy, is an integrating factor. For star. Okay, so these are the two conditions, okay? It's not really two conditions, they're two different things, right? It might have an integrating factor in two ways. One is if my minus nx divided by n gets rid of all the y's, or another one is if my minus nx divided by m is equal to g of y, meaning all the x's go away. Okay, so I would like us to try an example here. So we're going to solve the differential equation. And let's go ahead and call it star because I know I'm going to refer to it later. So here's our differential equation. 2x minus y squared dx plus xy dy is equal to 0. And suppose they're telling us in advance that x is positive. All right, let's go ahead and label these. This is m, and this is n, right? So this is the way these problems go, right? We're going to first test if it's exact. So what's my? My is equal to, you take the partial with respect to y, you get negative 2y. And what's nx equal to? Nx is y, and these are, of course, not equal to each other, right? So this implies that it is not exact. Now, that doesn't mean, though, that we can't make it exact. Maybe there is an integrating factor we can use. So let's go ahead and try my minus nx and divide it by, we're going to have to do it, first let's try to divide it by m. So we're going to do it both ways, right? I want to divide it by m, and I also want to take my minus nx, and I want to divide it by n to see if one or the other makes all of one variable go away. So first, what's my minus nx divided by m? Well, we get negative 2y minus y, and then divided by 2x minus y squared. This is negative 3y over 2x minus y squared, which is definitely not a function of x, right? Oh, sorry, that one needed to be a function of y, didn't it, right? When you divide it by m, yes, that needed to be a function of y. So it's clearly not. So let's just say this is not equal to g of y. Okay, so let's see what the other one is. What's my minus nx divided by n? Okay, so this would be negative 2y minus y divided by xy. This is looking promising. Negative 3y over xy, and these cancel, and we're left with negative 3 over x, which is equal to a function of x. What does that mean? This means that we have an integrating factor. So an integrating factor for star is, remember the way you find the integrating factor is e to the integral of that f of x that we got, so negative 3 over x dx. Okay, what would the integrating factor be then? This is e to the negative 3 ln x, which is just equal to x to the negative 3. So now we're going to multiply the entire equation star by x to the negative 3. So let's go to the next line for that. Multiplying star by x to the negative 3 yields what? So if we multiply it by x to the negative 3, we get the following. 2 over x squared, right? Because it's like we're dividing everything by x cubed. Minus y squared over x cubed dx plus, remember before we had xy, right? So we're going to divide that by x cubed, and so we end up with y over x squared dy is equal to 0. So we should have something exact right now. Okay? Can we test it? Well, let me go ahead and call this m. I don't want to call it m and n because we already called something else in this problem m and n. Okay? So let's go ahead and call this guy, let me call this guy m. Let me call it m1. And let me call this guy n1. So if we did this right, it should now be exact. So let's test it. What's m1y? Partial of m1 with respect to y. This is going to be negative 2y over x cubed, right? What would the partial of n1 be with respect to x? Partial of n1 with respect to x is going to equal, remember this is really the same as y x to the negative 2. So if you take the partial with respect to x, you get negative 2y x to the negative 3, which is the same as negative 2y over x cubed, and you notice that these two are the same. So this was just to verify that yes, if I were to call this guy star star, star star is now exact. Right? We just gave it a test and it passed. So now we're going to find our potential. So find phi, right? This is where what we're doing now. So remember, if the partial of phi with respect to x is equal to m1, this implies that phi is equal to the integral of m1 with respect to x. So it's going to be the integral of, let me write it this way, 2x to the negative 2 minus y squared x to the negative 3, right? I'm integrating that guy with respect to x. So if I integrate that guy with respect to x, I get 2x to the negative 1 over negative 1. And then if I add 1 to the other power, I get x to the negative 2 over negative 2, which becomes a positive. So plus y squared x to the negative 2 over 2. And then plus, we've got some unknown function of y. And what about the other guy? Partial of phi with respect to y, if we set that equal to n1, this means that phi is going to equal the integral of y over x squared with respect to y. So if we integrate y over x squared with respect to y, we end up with y squared over 2. So it essentially becomes y squared over 2x squared plus some unknown function of x. So if you set this guy equal to this guy, what do we notice? We didn't gain not that many new pieces, but we know that g of x must be this 2x to the negative 1 over negative 1, right? Because that guy doesn't appear in the other. So we end up with, this is going to equal negative 2 over x, right? And we know that h of y is 0 because there's no y parts in the second thing I circled, right? And so we know what phi is, right? This means that phi of xy is equal to just negative 2 over x plus y squared over 2x squared. So we're ready to solve the differential equation. This means that d of negative 2 over x plus y squared over 2x squared is equal to 0. This is now our differential equation, which means, so I should say, this is what we get if we rewrite this guy, right? And so you integrate both sides and you end up with negative 2 over x plus y squared over 2x squared equals c. This guy is our general solution. It is a bit of an involved process when you want to do the integrating factor, but this problem illustrates, how you do that more involved process when it's not exact, but you can make it exact with an integrating factor. All right, that concludes this video. I hope it was helpful. Thank you for watching.